Today, several different approaches exist to estimate camera poses and 3D geometry from a set of images. There's classical feature matching, which estimates poses and triangulates sparse 3D points from image-to-image correspondences. There are feed-forward models that directly predict camera poses and 3D point maps from a few images. And there is scene coordinate regression. Methods like ACE and ACE0 implicitly encode a 3D visual map into a neural network. Different from pre-trained feed-forward approaches, ACE-like models leverage a few minutes of lightweight training via backpropagation to extract poses and geometry from thousands of images or more. Often this works well. Scene coordinate regression utilizes multi-view constraints to converge to a consistent 3D representation with accurate camera poses. But sometimes, if multi-view constraints alone are insufficient, things go wrong and the reconstruction can completely degenerate, like in this example. But how can we tell? Why is this probably not the room we wanted to reconstruct? Parts of the scene look okay, but there are cameras floating in space and large parts of the 3D geometry are dispersed into infinity. This is very unlikely. And indeed, if we look at a histogram of reconstructed depth values, we see many scene coordinates being very far away from their camera. Definitely not what we would expect from an indoor room. So what can we do? Option number 1. If we had RGBD images as input, things would become very easy. For any predicted scene coordinate, we could project it to its corresponding mapping image and compare it with the measured depth at that pixel. During iterative reconstruction, we can pull the scene coordinate to where it should be. This works very well and essentially gives us an RGBD version of ACE0. But what if we do not have RGBD inputs? Option number 2. Even if we do not know the depth of individual pixels, across all images of a scene, we expect a certain distribution of depth values. Throughout iterative training, we can penalize significant divergence from plausible distributions. When we optimize the reconstruction loss, we also optimize scene-level statistics, which represent our prior knowledge about how reality works. In this case, our prior is handcrafted and yields results that are close to those we had when we knew the depth of the mapping images. Now, instead of handcrafting our priors, can we also learn them? Option number 3. Assume we have a large collection of scenes that were reconstructed correctly, in this case a dataset of indoor rooms. We can train a 3D generative model that encodes the general 3D layouts of such scenes. In our case, this is a 3D point cloud diffusion model that can generate plausible room layouts from Gaussian noise. When we reconstruct a scene using ACE, we use the 3D generative model to guide the scene coordinate regressor. In each training iteration, the generative prior nudges scene coordinates towards more plausible configurations, resulting in a good reconstruction using a prior that was not designed but trained from data. To combine our various priors with scene coordinate regression, we reinterpret the established training procedure as maximizing the probability of scene coordinate y, giving training poses and images. This allows us to decompose the probability into likelihood and prior, where the prior can take various forms within the same probabilistic framework. Thanks for listening.